Okay, but another thing is to say about relative humidity. Relative humidity. And relative humidity is the ratio of the amount of water vapor. Mind you, this is liquid water. Water vapor is liquid water in the air. These little drops there, they're suspended by the air molecules on that. Our clouds are not gaseous water, they are liquid water because you cannot see gaseous water. If you can see it, it's liquid. So always keep that in mind. If you can see it, it's liquid. All right? And it's the ratio of the amount of water vapor the air can hold on that. So how much it has versus how much it can hold. Relative humidity. Now humidity, if you just said humidity, that's how much water, like how many kilograms per cubic meter of water. Okay, that tells you how much water is in the air. Doesn't tell you how much water you could put in the air or how it's going to affect other things. That's relative humidity, which is a percent. Basically, it's the humidity versus how much it could hold. And that has to do with temperature. The warmer the air, the more water. Why is that? A couple of ways to visualize this. If I had a bunch of ping pong balls and I was keeping them in the air with two paddles, the more ping pong balls I have, what do I have to do with the paddles to keep them all in the air? I have to move them faster. Faster. Okay, faster, faster, faster. So I do that. It's kind of like this. If I keep one ball in the air, it doesn't take much. Watch, I can keep that ball in the air. Keep two balls in the air, not much. But if I want to keep three in the air, I got to move my hands much faster. I'm not doing very good on my juggling today. Like that. So you can see it takes me more effort. Now when you're saturated means I'm at 100% humidity. The air has all it's going to hold at a particular temperature. That's all it's going to have. So it all it can hold at that temperature. Now, because it's based on temperature, when it's cold out, do you think cold days have relatively high or low humidities? No. Well, depending on where you are. In California, you end up with relatively high humidities. Our high humidity time is in the winter. Our low humidity time is in the summer. It's kind of reverse for back east on that. And we can look at some things here. We're going to look at some places around on this. So we can go to the weather. There we go. All right. So notice today, this is Redwood City, I think. That's what it says. That's Hayward. That's across the bay. Let's call it Redwood City. Redwood City, notice our humidity right now is 87%. Notice when it's raining does not make it 100% humidity. All right? 87%. 87%. Now, if you were someplace hot, what would that 87% humidity feel like? Feel awful. Why don't we notice these high humidities in the winter? It's cold. Is your body trying to cool itself off? No. For the most part, your body is not trying to cool itself off. Now the thing is, when it reaches that saturation point, saturated, is there any room for any more water to go in the air? No. So when you sweat, is any of that sweat on your body, is it going to go anywhere? No. And if it doesn't go anywhere, is your body going to cool off? No. Miserable. And the higher the humidity, the slower that rate. And there's only so much water can be held. Well, you go someplace like Disney World in the summer. Now, during the day, kind of rotten, July, hot, humid. You think Sun's going to come down, it's going to get so much nicer. Now you do have the thing, when the sun goes down, are you getting hit by all that radiant energy anymore? Yeah, so that's one thing. Any of you have been to Disney World in the summer, when the sun goes down and it starts to cool off, does it get any better?
No.
Does it get worse? Because guess what? During the day, the humidity may have been at 90%. Were you still being cooled off? And now as the temperature starts to go down, what's happening to my relative humidity? It's going up, right? Because as the temperature goes down, it's going to hold as much water. Ooh. It gets to a point it gets saturation. When you get saturation, it's not going to take any more up. So your body all of a sudden is just like, oh, it just stays on you. And then it starts cooling off more. What's happening to that water that's already in the air? It starts to seaward. Condense. Starts to go out on everything. That's why everything gets wet. We call that dew. I mean, if you're not doing very physical things at night, which is what we used to do at the academy, we did our PT in the morning. Talk about that. We drilled at night. We march out there with our rifles. 13.5 pounds of misery. But you get done with, when you get in after that, so you'll be drilling from about 8 till 9, 9:30. On that, you get back and you take your shoes, you pour the water out of it. The water, as it ran down your body into your shoes. And sweat. Yeah, I know, it's not pleasant. We had no air conditioning in our dormitory. No air conditioning. The heat, no air conditioning. Okay, so, but in the morning though, you get up in the morning and it starts to heat up. Is all that water going to go immediately into the air? No. Eventually, all that dew does evaporate and it does go up in the air. So if you're going to do physical activity, when do you go out? Right after the sun comes up. Which is what we did when we were at the academy. We'd have PT right at dawn, about 6 a.m. So we'd have at 6 a.m. Just as the sun came up, it starts to heat up, but we did most of our heavy physical activity then on that. Well, you look some other places around. I need to call up a few other places on this. So we call it Chicago. Notice its humidity right now. Very low. 37% humidity. 34 degrees. Appears to be snowing in Chicago. Even in Orlando, notice what's the humidity right now? It's 34%. What time of year should you go to Disney World? Now. Now. On that. Not going to be nice to me. There we go. Cape Town. This is in South Africa. Notice it's night there. But no, 73% humidity. But in Cape Town, this is the southern tip of Africa. It's summer. Summer there. Summer. Let's see. Trouble. It's we'll check. I can spell right. Did I misspell it? What? A-I. Really? I don't think so. No, A-I. Anyone know how to spell? Oh, there we go. Okay, so it's daylight there. It's 84 degrees, but only 40% humidity. Summer there. Nice day. Look, it's going to be 90s on that. Nice day there. So place where it would normally be humid. And this is summer. So 88% humidity in Sydney. Summertime. Yeah, this is 5:59 a.m. in Sydney. It's summer. Now see this right here, it says dew point, 64 degrees. Basically that's the temperature it would have to get down to right now to get to, for dew to form. In other words, if the temperature got down to 66 degrees, it's 68 right now, water would start coming out. Notice it says feels like 70. The humidity will make it feel like 70 there. If we went back to Chicago, let's see, there's other reasons for that. So notice in Chicago it's 34, it feels like 34 because the wind's barely blowing. But notice the dew point here, 10 degrees Fahrenheit. Of course, are we going to get dew at 10 degrees Fahrenheit? No. No. Wind's not blowing very hard. Where? I can't even spell that, but that's all we need to say. Well, we can do Mexico City. Mexico City right now, 40% humidity. Basically, it's a desert, so 65 degrees. Very dry climate. All right. Well, you can see that. That was Redwood City. Now there is one process we didn't talk about. There we talked about melting, condensing, boiling, evaporation, things like that. Last one we need to talk about sublimation. This is the process of going from a solid directly to a gas. It's also this is also the term we use to go from a gas to a solid. We also call that sublimation on that. Our example here would be dry ice, which is carbon dioxide. Solid carbon dioxide at atmospheric pressure. Carbon dioxide will go straight from a solid to a gas. It will not first become a liquid. It will not first become a liquid. Those other times, this is kind of how a frost-free refrigerator works. Is it causes the ice to sublime away. It goes from a solid to a gas in your refrigerator, in your freezer. That's why sometimes you leave your ice cube trays, the older ones, the newer ones don't do it as badly. But it used to be when they first came out, if you left uncovered ice cube trays, you come back, pull out your ice cube tray, there'd be no ice. Because the freezer can't tell the difference between ice inside the ice box, just that it needs to get rid of, and ice cubes in a tray. You can't tell the difference on that. So we're going to talk about two things. This is not in the book. You need to draw these diagrams. Pressure temperature diagram. We're going to draw two. One for water, one for everything else. Water's is different. Water's is different. So, and this tells us it's certain pressure and temperature combinations. Now, we live at 1 atmosphere of pressure. But what happens when you go up in the mountains? What happens to the air pressure then? It goes down. So it's other things that happen. So basically here, looks like this. You have these lines. And the slope of this line is very important. Now this one goes up and to the right. All right. So this region, at these temperature and pressure combinations, you get solids. At these, you get liquids, and here you get gas. Along this line is where sublimation occurs. This is sublimation. In other words, you're going to have solids and gases together here. Sublimation. This line is our melting and freezing line. So you're going to have solid and liquid together. When you're on the line, there's going to be two states. Condense and boil along that line. Sublimation. Where the three intersect is called the triple point. All three phases are together. And they're going back and forth. So solid to liquid, liquid to gas, gas to solid, solid to gas. And you have this all going on. Remember, we talked about that when we talked about Kelvin temperature, right? That there's the triple point. So this combination of pressure and temperature, and this is different for every substance, you're going to have that together. So you have a diagram like this for every substance. Now think about this. For most materials, if I had this, say this is propane at 20 degrees, 1 atmosphere, which is basically what it is in this room. It's a gas. But as I start to increase the pressure, first it will become a liquid. Then it will become a solid, and the more pressure I put on it, the more solid it gets. Remember our bottle? Whenever you shook it, you can hear the solid in there. Under pressure, that gas is a liquid, but some of it is also turned into a solid. If I put more and more pressure on this, would it be possible to get this whole thing to be solid? Yes, it would. And that's what happens to most things. If you put more pressure on it, it will become more solid. All right? Anyone need more time on this diagram? So let's go to water. Water. Again, water. Different than everything else. Different from everything else. Now, the first two are the same. They look the same. But for water, instead up and to the right, it goes up and to the left. So we still have our solid, liquid, gas. Now, if we are at 1 atmosphere, now on this chart, here's 1 atmosphere. Right there would be 0 degrees Celsius. (100 degrees Celsius). Now, notice if I went into the mountains, though. If I go in the mountains, what happens to my air pressure? It goes down. Now, notice when you go in the mountains, what happens to my boiling temperature? Boiling temperature goes down. Did we already know that? Yeah, if you've ever read the side of your macaroni and cheese package, it has high altitude instructions because the temperature goes down. If you've ever tried to make a hot cup of coffee in the mountains, it's not quite as hot. You have to boil it. Like if you're trying to boil water, it just doesn't get as hot because the air pressure on that. It's also why more likely, if we don't see pressure cookers too much anymore. Some people have them. Pressure cookers. Why do people have pressure cookers? Well, when you put them under pressure, if I increase the pressure, what happens to the boiling point? It goes up, which means I can make the water get hotter. So people have pressure cookers to make it hotter to cook food quicker. Pressure cookers have been replaced by the microwave. However, if you are in the mountains, a lot of people in the mountains, I bet you they still have pressure cookers because they can't get up to that 100 degrees, things like that. So they still do things like that. Some people have them. But notice what happens to the freezing point and melting point of water when you go in the mountains. Not only does the boiling point go down, the freezing point goes up. In other words, water will freeze in the mountains at a higher temperature than it does here. It boils at a lower temperature, but it freezes at a higher temperature. This is unique about water. When you remove pressure, the melting point goes down. Most substances, when you reduce pressure, the melting point goes up for water. Most substances, notice if I take pressure off, it goes down. You know, one way to melt something is I can take, instead of heating it up, I can take the pressure off. If I lower the pressure, it's going to melt. Water will not do that. You remove pressure from water, it freezes. All right? And it's solid. It also means if I put, notice, if I have solid water and I put it under pressure, most substances become more solid, right? Water becomes a liquid, unique among substances. By the way, it's this property of water. Let's think about deep in the ocean. Now, if for whatever reason I had a baggie of mercury, liquid at room temperature, right? And I started letting it go in the bottom of the ocean. You know, if I keep it at room temperature, so I'm keeping it, I'm keeping it at 20 degrees Celsius, but I'm laying pressure on it, eventually as I go down the ocean, what's going to happen to that mercury? It's going to go solid, because I increase the pressure on it to go solid. But water, if I took solid water, and I bring it down to the ocean, as the pressure goes on, even though it's getting cold, the bottom of the ocean is usually about 1 or 2 degrees Fahrenheit. Temperature of the bottom of the ocean, 1 or 2 degrees Fahrenheit. So I bring it down to the bottom of the ocean, it's going to melt. To melt. Even fresh water to melt. Pressure. Which is good because if water got solid under pressure, most of the oceans would be what? The ice would be frozen. Because of pressure. Not because of temperature, because of pressure. Again, a unique property of water keeps the Earth from becoming a big giant ice ball. I mean, if our oceans were made out of any other substance than water, they'd mostly be ice. The idea of, they think, well, if there's oceans of methane on this other moon, well, the bottom of those oceans of methane are going to be what? Solid. I don't even have to look on the other side. I just have to know that, well, the farther you go down in any liquid, the pressure goes up because of the weight of the liquid above it. And this is physics. Just like I don't need to be in the middle of the sun to know there's no light. I know what plasma is made out of. Things like that. I just have to apply what I know about physics. But this allows something called regulation. By the way, this word I've seen pronounced actually regulation and regulation, both. RG and in English it should be regulation because of the E. Usually a G followed by an E, it's a J sound. But I've also heard it in English. But I've also heard it pronounced regulation. So I've heard both. And I think the dictionary, I've looked it up, it has actually both in it. But this is solid water turning to liquid under pressure. Again, water is the only one that does this. So if I have this wire, if I start this wire at the top, it will slowly move through this ice block and come out the bottom. What happens is underneath that wire, very high pressure causes the ice, the solid, to become a liquid. Well, can that solid support the wire? No, so it melts and the water basically sinks in the water, in the liquid water. Well, as soon as it sinks, the pressure is released and that liquid water becomes a solid again. And then the next layer melts, and it goes through, and it keeps moving, until it goes out the bottom. By the way, there is a myth that this is how ice skates work. Ice skates do not work like this. It is true that ice skates, now figure skates have two edges. I think hockey skates only have one edge. But figure skates have two edges. And people say, well, because you put all this pressure on, it causes a liquid, and this is what causes the lubricant for skating. That is not true. When you are at the skating rink, on top of the ice is this very, very microscopically thin layer of liquid water. Liquid water. It's that liquid water that makes the ice so slippery. Because if you needed to have that ice skate to make it slippery, you walked out there in your tennis shoes. Should it be slippery when you're in your tennis shoes? Because your tennis shoes can't put the pressure on to make it turn into a liquid. In other words, your tennis shoes would not be able to cause regulation if that's what makes ice slippery. Is ice slippery when you just walk on your shoes? Yeah. The thing is, if you get the ice cold enough, now natural ice, if you're out in really cold areas, even this little liquid layer freezes. Because it's really cold out, you can walk on ice. It's not all that difficult. This one's really cold. It never really gets that cold around here, even in Sierras. It's like Antarctic cold. All right, questions? That ends chapter 23. So we get to chapter 24 here. It doesn't take long. Which leads us to the first law. The yes, you can break even law. First law of thermodynamics is just a restatement of the law of conservation of energy. Law of conservation of energy. And it states whenever heat is added to a system, it transfers to an equal amount of some other form of energy. Generally, we're talking about work. Now, what we're talking about, this relates to the change in internal energy of a substance and work. What we're really looking at are changes in the internal energy. And by the way, how do we measure changes in internal energy? It comes out as a change in what? By change in internal energy, it causes a change in the object's what? Anybody remember? Keyword. Temperature. Yeah, by increase internal energy, temperature goes up. By decrease internal energy, temperature goes down. So my internal energy and actually we're talking about a change in internal energy, which would be delta U. Delta U equals heat plus work. In other words, equals Q plus W. We have some sign conventions and some grammatically. You got to be very clear how you state that. Heat is easy, work not as much so. On this. Anybody need more time? So, how much heat you do, how much work you do on a system, how much work is done by a system. Things like that. Where is the energy going to? Coming in, going out, things like that. Good? Good? So we have a sign convention. This is really important. Like I said, now if I positive Q means I'm adding heat, which is what we did since day one. That's easy. I add heat, temperature goes up, internal energy goes up. MC delta T, ML. That's right. Negative Q, negative heat, or sign negative, means we're losing heat energy. Delta U is going down. That's easy. Negative W. W is work is negative. Work done by the system. Delta U increases. This means usually a change in volume. Changes in volume. That's usually what we're talking about, work. Because a lot of times we're dealing with gas systems. That's like a piston. When it expands, when you expand up, that thermal energy is converted to work. The internal energy is converted to work, and the fluid cools down. An example of that: if you ever have gone camping and you have your propane lantern, and I'm running my propane lantern, what happens to the bottle? It's what? It doesn't get hotter. It gets cold. It gets really cold. Why is that? Because the internal energy inside there, we're not adding any heat to it, but it's expanding. So the fluid, the gas, has to expand. To expand, it has to do work, right? Because when you release the valve, it allows the air to expand. As it expands, it absorbs energy from what's left inside. In other words, the internal energy goes down, and the whole bottle gets really cold. In fact, you can even get, if you're using enough, we'll get frost on the outside of the bottle, because it'll cause water not only to condense but freeze on the outside of your bottle. Conversely, if positive work means work done on the system, and you define what the system is, this be like a bicycle pump. If you've ever used a bicycle pump and you're pumping and pumping and pumping, what happens to the barrel of the pump? It's warm. It's warm. Grab it, it'll be hot. You know, if you're pumping, because as you're doing work, you're putting energy into the fluid, the air. And that air will transfer to the side, but you're doing work on the fluid, the internal energy goes up, it gets hot. Anyone need more time? And actually we're going to stop there. Stop there.